time we should get started. Today we have Diego from Cornell. Diego has worked in several areas, interesting now. He started working as a video astronomer early on. He did his PhD in Harvard, where he was working with our ray, using Arico, but not in cosmology simulations. You will see some of his work in Circumbinary. And now he moved as a postdoc a couple of years ago to Cornell. He's been working mostly on dynamics and also gas dynamics. Show us some results.
Thanks, Cristóbal. Yes, I'll tell you a bit about two projects, one recent and one ongoing. One is on circumbinary planet dynamics, and the last one, I hope to get enough time to talk about the recent work I've been doing with moving mesh simulations of circumbinary gas, presumably both connected via the process of planet formation. So basically, just to start, I'll just motivate this topic with just commenting on how frequent circumbinary systems are. The topic that brings us today is planets and disks, circumbinary planets in particular here. Perhaps amongst the most interesting findings or surprising findings of Kepler, circumbinary planets do form. That's already a finding. They form quite efficiently according to some statistical estimates. Perhaps at the Neptune-sized planet, perhaps as efficiently as single stars, if you assume coplanarity. If you assume they can be anywhere, they would form at a striking rate of almost 50%, according to statistical estimates. The second topic, which is also interesting and perhaps connected evolutionary to the planets, is that of protoplanetary disks around T-Tauri spectroscopic binaries. Just two very interesting examples here in the Taurus region, UZ tau east and DQ tau. They're compact, a few days, 10 days, 20 days period, eccentric, different mass ratios, and they have very, very bright disks. That could imply, it's not necessarily a true conversion between luminosity and mass, but they could be very massive, which could explain, according to some authors, why these planets form so easily, or apparently easily. So for completeness, there are other systems, like in our own solar system, the very interesting Pluto-Charon system. It's a binary dwarf planet with 4 additional tiny moons. Thanks to the New Horizons spacecraft, now we have a full familiar portrait of these 6 bodies. And a very interesting, important topic, I'm not going to talk much about it or nothing at all, except unless you replace my simulations, replace the stars with black holes, but that is the supermassive binary black holes in the centers of recently merged galaxies. We believe these must exist since galaxies merge, and elliptical galaxies do not seem to have more than a supermassive black hole. So a natural consequence of the merger is that the black holes themselves merge. So they must exist. However, we have trouble finding them. There are a few very interesting candidates like this one here in this Seaford galaxy. However, the details of how these black holes merge is not quite clear, especially because we're not quite sure how to make them close enough such that gravitational radiation can take over and merge them. So maybe the gas dynamics themselves can play a role in the merger. As I said before, this is my topic. I will spend most of the talk talking about the planets and the last 10, 15 minutes talking about the gas simulations. So circumbinary planets. I really hate this, but I put it anyway. I love Star Wars, but I like to keep science and sci-fi separated. Some authors I respect very much insist in calling them Tatooine planets. Luckily, it hasn't caught on yet. So I'm going to call them circumbinary planets. But if you talk to the press and the media, they really, really love bringing it, when you bring this up. Luke Skywalker in the desert. Anyway, so I mentioned briefly that their planet-bearing frequency in this system seems to be very high, 10% according to Armstrong et al. Based on the 10 circumbinary planets we know around 8 system. I think Kepler-47 has 3 planets, I believe. They're all very coplanar, so they're all detected via the transit method. So obviously, there's a strong selection bias in favor of detecting systems that are coplanar. Formation scenario would, in a disk and subsequent disk migration, would suggest the system should be coplanar. However, given the observational biases, we cannot be sure yet if indeed all the circumbinary planets are coplanar. And I will go back to this topic because it's a main point in my talk. There are a few planets that are mildly misaligned, I think 3 degrees. That's the case of Kepler 413. It's like 3 degrees, so it's misaligned enough that it will precess. Its orbital angular momentum will precess around the orbital angular momentum of the binary. So it goes in and out of transiting windows. So it will stop transiting soon, and in a couple of decades, it will begin transiting again. So there's a population we could be missing, indeed, if they're misaligned. Yes. So there, amongst the puzzles, the one that caught my attention is the following. For the known Kepler circumbinary planets, the planet-bearing frequency seems to be high. However, there's a steep cutoff beyond below binary periods of 7 days. Perhaps is that statistically significant? It is very much. This is the same result here, just to highlight the known Kepler circumbinary planets. These are the planets, and these are the binary periods. And there's a minimum at 7.5 days. And this is statistically significant because lots and lots of the Kepler's eclipsing binaries that were in the catalog are actually of periods shorter than 5 days. And this is just, I downloaded the database a while back. So just these are the period distribution of Kepler transiting eclipsing binaries. And in green, I put those that have periods of less than 5 days. So there's around 50% of them, and they don't have any planets. It's just actually, these are the ones, the range of periods that do show planets. If planets were, I'm sorry? Coplanar planets and closing planets, yes. So if you extended the logic of these planets, are coplanar and very close to the stability limit, which is a few times the semi-major axis of the binary, if you could extend the logic to these planets, they should have deep transit signatures and they should transit very, very often. So if they are there and they share these properties, they should be easily detectable. So that's the two options. They're not there, or they're in orbits that we cannot detect via transits.
But if they are there and coplanar and transiting, the transit will be highly variable, right? Because the relations are bounded pretty.
Well, as long as the binaries are point masses, the problem should scale.
But the transit time will not be periodic.
If they're coplanar, yeah, it would be periodic. It should scale roughly in the same case as with the binaries that are of wider separation. It is not exactly a secular problem, if that's what you're asking.
No, I meant that the transit time will be tighter because the center of mass. If you go around the center of mass periodically, you don't go around the star periodically. So the transit to the star.
Oh, okay, yeah. Yeah, I see what you're saying. Yeah, that is taken into account. So they like this type of data. They show mutual eclipses of the binary and the eclipse and the transit across each star. Yeah, and that is not periodic in each transit. It's periodic in when the planet transits the center of mass. Yes, but that is taken into account in the data. But there's some eclipse timing variation, but that's very mild for the baseline of most of these observations. So that's a second order correction. But as long as you're not too close to, I mean, the problem should scale roughly independently of the separation of the binary. But if they're there and we share the logic that they're very close to stability boundary, they should leave a very clear imprint, and they should happen very often. So statistically, those transits should be very easily detectable. So the question to ask is, are these binaries normal or not? And this relates to the paper we're discussing earlier today. There's a Borkovits archive posting that discusses the frequency of binaries and triples in the Kepler data. So I'll on and off mention that since I haven't had time to read the paper. But at least until a year ago, and consistently with 2 decades of data, there seems to be a bump in the period distribution of compact or semi-compact binaries. So what I'm showing here is a plot from Tokovinin, and that it takes the periods of binaries of certain period, either they're in triples or not, and the solid line is the data showing a bump at very short periods. There's a lot of curves, but please pay attention just to the dashed line, the simulated data, and the solid line. The simulated data comes from the log normal distribution of periods. It's surprisingly successful over several orders of magnitude in period of the binary and of multiples. Nevertheless, it fails significantly at short periods. So these people have referred to this as the overdensity of short period binaries. Again, that's an overlap with the planets that are in Kepler binaries. This is another plot. This is a little bit older by the same author. This shows the fraction of binaries as a function of period that have a tertiary companion. This is not eclipsing data. This is rate of velocity and spectroscopic data. This is for spectroscopic binaries. So for very compact binaries, the fraction of stars that have evidence for a tertiary companion is almost 100%. So what I'm trying to build up here is the fact that these binaries, those that lack Kepler planets, are probably not normal binaries. And again, there's a comment here about the paper that appeared last night. In contrast with the spectroscopic binaries, the Kepler binaries have a total tertiary fraction of about 8%, 9%, and they claim a deficit of triples in a certain period of the range of periods.
It has to do with the coplanarity.
Yeah. So I mean, we're measuring different things. It's just like, but we're completing the parameter space with these two. There's not necessarily yet any contradiction between the data, but for the first time, we're finding via eclipse timing variation a population of triples, and we were constrained via proper motions and spectroscopic binaries before.
This
so
is not companion.
Kepler's
No, this one these triples are not companion.
oh, this one's here.
No, the next one.
They did everything they had. I mean, the eclipse timing variation is modulated. It depends on the angle, but it's not constrained by having coplanarity. So as long as you have a modulation in the timing of the eclipses, and you have an orbit that you can resolve in time, it doesn't matter what the tertiary is. Yes. Yeah. So this brings me up to the Kozai cycles with tidal friction. We have a couple of experts in the audience. Basically, to the simplest approximation, when you have a triple with misaligned angular momenta, the outer companion of the orbit, that is the triple, which has most of the angular momentum, would cause oscillations in eccentricity and inclination of the inner binary, such that to the quadruple level of approximation, this quantity is constant. So the inner pair, in our case, the inner binary, will oscillate in eccentricity and inclination. The key point here is that these binaries come very close to a few stellar radii from each other. So if there's dissipation and tides, you lose orbital energy, and eventually the binary will shrink and circularize again, leaving a very compact binary. Just plot here is just to show how popular this mechanism has become in the last decade, showing that these two seminal papers have increased the number of citations just exponentially. So this was suggested several times in the last couple of decades as a possible mechanism for the evolution of compact binaries. This plot I stole from Fabric and Tremaine in 2007. They did a Monte Carlo experiment of this mechanism, evolving from that semi-empirical log normal distribution of periods, putting inner binaries and outer tertiaries, triggering the Kozai cycles, and see what happens to the binaries. So first, they did this with just the binaries, see if tidal evolution changes the distribution of periods. And if you have to look really up close to see any change. However, once you put a tertiary, the initial log normal distribution of period gets reshuffled. And you have a peak, which is consistent with the peak of the Tocqueville paper, the short period binary peak, that in its majority comes from a relocation of binaries that originally had 100-day periods down to very short periods, 2-3 days. So what is striking here, or interesting to me, is that we're converting 100-day period binaries, 50-day period binaries, which are of the kind that host Kepler planets, into 2-day period binaries, which are the kind that doesn't. So the natural question to ask for me is, what if these binaries did have a planet what happens to the planet after the binary goes under this triple evolution. Again, this is, I stole this from the
The third object, was it also drawn from the same distribution?
Yeah, so this seems to be worked very well. And I don't know the reason, but if you draw two periods, essentially, draw with replacement from a log normal distribution, the only caveat is to make sure under some criterion that it's stable. But if it satisfies stability criterion, it's a valid triple. And it works, at least to the data available at 2007, I would say surprisingly well for the observed population of hierarchical multiples.
But not all the planetary systems would survive. Maybe the triple system is stable, but not all the planetary systems.
Exactly. So that's what I'm trying to test. Right, so what is pretty clear intuitively is that if you have circumstellar systems and the binary shrinks, you have orbit crossing, those planets are going to get ejected. What is not so obvious is if you have, to begin with, a circumbinary planet around a binary with 80 days, 50 days, which is consistent with the Kepler sample. If you shrink that to a 2-day binary, what happens to that planet? So that's the calculation I'm going to show you. So this is from last night's paper. They find a peak in the inclination that they identify as an evidence for tidal friction, although they're quite conservative about the assumptions. Anyway, so this is what it looks, a binary that shrinks looks like under this Kozai cycles with tidal friction. Please look at the blue line in this case. This is the inclination of the inner binary. The first few secular cycles, you see inclination and eccentricity, in y minus eccentricity and inclination. Until tidal friction kicks in, you have orbital decay. The angle freezes at some inclination, and the eccentricity goes to 0. This is the same system, but I'm showing in blue the semi-major axis. Okay, so during the first few Kozai cycles, it's essentially constant. However, when tidal friction kicks in, the semi-major axis shrinks by more than an order of magnitude. So this goes from a binary that is 0.3 AU, so a period of 80 days, I believe, to 0.25 AU, a couple of days. The green line is pericenter. So every time you have pericenter, you're dissipating energy. So all I'm adding to the mix is a fourth body and integrate the same secular equations, but with a fourth body around the inner binary. So again, try to turn a Kepler kind binary into a compact binary. What happens to the planet? By the way, according to the same databases by Tokovinen, the likelihood of having a tertiary companion at these separations is still 20%. So it's still pretty likely that these binaries can have a triple. The question is, if they do have a planet, what happens to the planet? So I'll initialize this problem like this, just the same way a secular triple is initialized, and I put a planet coplanar with a binary. So I'm trying to be as consistent as possible with the Kepler system. Is the initial condition reasonable? Well, as long as the planet is close enough to the binary, it will be safe. And so I just introduced here the concept of Laplace radius. Essentially, the planet is subject to two non-Keplerian frequencies. One is coming from the binary. There's not a Keplerian potential. And the other one is coming from the tertiary. And what you want to happen is that the precession of the planet is dominated by the binary only, such that the external companion is entirely invisible. So these are the two frequencies to quadruple order, the effect of the inner binary, the effect of the outer companion. If you equate them, you get a distance that you can identify in the literature as the Laplace radius. As long as the binary is within this distance, the planet is within this distance from the binary, the planet is protected. So no Kozai effects, no Kozai oscillations will happen to the planet as long as it's protected by the binary. So I'm going to, in more precise terms, we integrate the equations of motions of a planet under the presence of this Hamiltonian, this disturbing function, with the detail that the Hamiltonian itself is varying in time because the tertiary is making the binary evolve. So you have all this angular momentum vector that are affecting the planet, and they are evolving themselves. Okay, and just I call your attention to the semi-major axis of the binary, which is crucial in the evolution of the planet. Anyway, so this is one example. Same as before, the binary is shrinking via cosine cycles with tidal friction, but there's a blue line, which is the evolution of the planet. So in the early stages, the planet is following adiabatically the inclination of the binary because it's within the Laplace radius, it's protected. So what happens here is that the binary itself is undergoing its cosine lead of cycles, moving in inclination and in eccentricity, and the binary simply follows adiabatically what the planet follows what the binary is doing, regardless of the tertiary. However, as the binary loses energy, its semi-major axis decreases, it starts losing influence over the planet, and at some point they decouple. The planet in this circumstance continues to be circular at all times, but at some point they decouple in evolution, in the inclination evolution, and they have 30 degrees separation difference. So this would make this planet undetectable because it would be misaligned, but it would still be there. So I just repeat this a few times and compute where in inclination these planets end up. So this x-axis is the original semi-major axis of the planet, and the y-axis is the inclination. Here's the initial one. I evolve all these systems, and they all fall systematically and monotonically in a curve that grows or decreases, but grows with respect to the final inclination of the binary. So the further out you put the planet originally, the more misaligned will be with the final inclination of the planet, of the binary. So I will show you that this, if you put the initial planets on a red curve here, which is analytic, they should all land on this orange curve, which is also analytic. And I will spend a couple of slides explaining what these two curves are and how, if you start the planets here, in many cases, they will smoothly follow the evolution of the curve to land here, meaning that all these planets will be safe, except that they will be misaligned with the binary at the end of the evolution. I've talked a lot, so I would like to make a pause here for questions.
So this IPL is measured relative to?
I'm sorry?
IPL.
Oh, yeah, it's measured with respect to the outer triple, which is cast most of the angular momentum, so I consider it to be fixed.
But this is standing information relative to?
Yeah, exactly. So I consider the tertiary orientation as the global z-axis. Yeah.
And what is the inclination relative to the binary? Isn't that what matters for Kepler?
Right, so the inclination of the binary initially is here,
Yes.
and finally is here. So they start all coplanar, but the green line that I showed before, but not, yeah, that green line is the final.
The question is just when does the decoupling happen?
Yeah, that's
And is
one.
there any tidal dissipation in the planets?
No, I mean, you're pretty far from any Roche radius of the system, so yeah. So yeah, I will just explain what these curves are, just it's kind of interesting. So I talked about these frequencies, these precession frequencies. So in this system, you have a misaligned binary with a triple, call them angular momentum in, angular momentum out, and angular momentum planet is somewhere in between. If the inner binary dominates, you should precess around the inner binary. If the outer tertiary dominates, you should precess around the outer binary. And in general, you should precess about something in between those two things. So the key thing is that, you can notice here, this one depends on AN. So as the binary shrinks, the influence of the binary will shrink as well. So you should go, ideally, smoothly from this regime to this regime, which is illustrated by this cartoon, with the caveat that L in is also precessing around L out. So they have a background, so that's what I try to put in terms of a Hamiltonian, that is a background Hamiltonian that is evolving slowly, and which I've tried to represent here. So there's a third frequency, which is the precession of the binary around the tertiary. So you have three frequencies that are competing all together. So here I'm plotting the three frequencies as a function of AN. Two of them decrease with AN or increase with AN, and one of them is constant, this one. So what I'm showing here is the planet originally is dominated by the blue frequency corresponding to the binary. It's above the yellow frequency. However, since this one depends on AN, as the binary shrinks, that is, the time axis goes opposite to the AN axis, at some point those two frequencies will cross, and you go from the binary-dominated regime to the companion dominated regime until they stop. This is when circularization happens. I'll put the third frequency here in green to show that it's very much smaller than the other two. And this is the rate at which the Hamiltonian varies, to show that it's much shorter than any other frequency, and therefore the system can evolve adiabatically. So, yeah, the background Hamiltonian evolves very slowly. So again, the transition from this regime to this regime should happen smoothly, and the planet should oscillate around an equilibrium solution always, no matter what the equilibrium solution is, provided it's a stable equilibrium. So this is another example of how to plot the Hamiltonian I showed before. You start with Hamiltonian, the planet very close to the angular momentum of the binary, and as you decrease the influence of the binary or increase the influence of the tertiary, this equilibrium point moves smoothly. So if the system is adiabatic, if you start with a test particle moving around the equilibrium, you'll follow adiabatically the equilibrium until the equilibrium finds another configuration, which is orientation with the outer binary. Okay. So again, what I'm showing here is grabbing the background Hamiltonian and cranking up the influence of the tertiary, and see how the equilibrium point smoothly follows the new configuration. This is another way of representing the same thing. This is called the Laplace surface. Dan Tamayo did a good work on this topic. Essentially, if you being very close to the binary is equivalent to having zero influence from the tertiary. As the planet moves out, or as the binary shrinks, you should move smoothly along this curve until you align with the outer companion. The only caveat is, and this is what this dashed portion of the solution tries to represent, is that this equilibrium can be unstable. So what happens is that you follow adiabatically a solution, you've reached a bifurcation, adiabaticity is broken. And if that happens, then the planet is in danger. Otherwise, it should follow. These are different Laplace curves for different obliquities or mutual inclinations. So if the inner binary with respect to the tertiary is 80 degrees, you have a sharp transition between alignment with the binary, you cross the Laplace radius, alignment with the tertiary. And there's all this danger zone in which the Laplace surface is unstable. Below 60 degrees, the Laplace surface is stable at all times. So in principle, the planet should follow nicely.
Is there critical inclinations for the Cornell?
Yeah. Yeah.
So there's not all these curves.
Although these curves are valid, but not all these curves will be populated because the binary would not shrink at all. So the planet would stay where it is, yes. So above 40 is what we're interested in. And actually, probably in practice, we care about something even above 40, about 60 or 70, because the maximum eccentricity of the cosine mechanism it depends on inclination. So if you don't reach very high eccentricities, you're not going to dissipate energy, and you're going to cosi for the edge of the universe without shrinking the binary. So the planet will always stay there anyway. So this is the same plot I showed before, but with more information, showing the evolution of the binary in eccentricity, evolution of the binary inclination, and in blue, the planet. And I added, on top of the semi-major axis of the planet and the semi-major axis of the binary, what the Laplace radius is doing. So indeed, the decoupling happens when you're crossing that critical radius. So this decoupling that happens toward the end is at the point in which the planet goes from being dominated by the binary to being dominated by the companion.
These are pretty long time scales, huh?
Yeah, yeah, so pretty long time scales. So yeah, 10 to the 9, 10 to the 10 years, very depending on the tidal Q that you put in. This is a low inclination. So you touch a sensitive point because for this to happen without reaching this bifurcation, you need low inclinations, which means that if you want, it will take a long time to circularize.
Right.
If you put this at 88, the time scale might be 10 to the 7, but you run into this part in which the Laplace surface is unstable. So this mechanism produces two results, and I'm advancing the conclusion. If you run into the unstable branch, the planet might get kicked out. If you never run into a stable branch, the planet will become monotonically misaligned with distance, and it will be hard to detect. So just the same plot I showed before, but now with labels. That curve is the Laplace surface at the initial condition. That curve is the Laplace surface when the binary has finally circularized, and the planet all the initial conditions that I tried land where they should land, meaning that there was a smooth solution in between. But as you ask me now, what happens at higher inclination, the story is more complicated. The evolution, this is the same plot I showed before, but a triple with eccentricity of 83. The evolution initially is the same, adiabatic in inclination, planet remains circular. However, at some point, when you cross the Laplace radius, the eccentricity grows exponentially. At this point, the planet should get ejected. It will get excited, it will go inside the binary and get ejected or collide into the stars. So if you do repeat the same experiment, the dynamics are much richer. If you start very close to the binary to begin with, you can still land on the Laplace surface on average. So what I find is, what I think should be still a bifurcation, but the planet finds still an equilibrium, and it oscillates around the equilibrium with finite amplitude. The planet oscillates. These are what the error bars represent, an equilibrium that is very close to the Laplace surface. However, very close to this region here, all these planets have eccentricity growth exponentially. And all those, although this is a secular calculation, all those I deem them as ejected or collided with the stars. So indeed, and this is inconsistent with some other M-body experiments of the similar problem, the shrinkage of the binary does eject efficiently many planets if they cross the Laplace radius. However, and this is subject to the uncertainties in Untitled Q, if you can circularize the binary with a low inclination triple, those planets could survive. And the prediction is that the misalignment of the planet with the binary grows with the distance from the binary. So this is a cartoon, what happens. This is the original system. We shrink it. And the very shrinkage mechanism is the one causing the misalignment and making these planets invisible to transit detections.
So if we assume that Q is for all stars, then your mechanism is, to some extent, suggesting that you can actually populate the Laplace surface for the longer period, short period binaries. Is that true? The ones that actually take longest
right.
to migrate, so the process is actually dividing.
Oh, right. If they're still decaying, and not fully circular, but they could still be undergoing orbital decay, yeah, those are the candidates to be the most gentle to not having ejected their planets, yes. If there's a spread in tidal Q, for example.
Right.
Yeah.
So you could find this spectroscopically, right?
You mean RV?
Yeah.
Yes. Well, the main candidate, and I did a calculation for Eclipse timing variation rather than RV, which is the paper that I mentioned earlier in the talk. It's just the same principle, but except that you, instead of looking for the Doppler effect in the binary and how that is modulated, you measure the shift in subsequent eclipses and see if there's a trend, sinusoidal trend. The baseline would be short. It would be a year or months, because that's a period of the planet. But the amplitude depends on the mass of the planet. So a rough calculation shows me that it's a few seconds. Not impossible, but with cadence of like measurements every 30 minutes, not really doable. But not outside the reach of astronomy. But yeah, it's a difficult detection for Neptune mass planets. Yeah. And I want to check the time. Does it end at 3:30 or at 3? Okay. I mean 3:30, yeah, 3:10, yeah. 3, okay, yeah. So yeah, summary, I think I've mentioned this. There are other caveats that I haven't mentioned. The mass of the planet might affect what actually happens. So this is something we explored in our paper, and also the other authors that were working on this problem explored. The planet itself, although it has a very little mass, it can also shield the Kozai cycles in the binary. So there's a maximum mass which would allow for this mechanism. But the overall conclusion is that these planets may exist, and if they do exist, they should be very misaligned around compact binaries. Alternatively, inverting the argument, if just to strengthen the origin of these compact binaries, if we can't ever detect planets around these binaries is yet another support of the hypothesis that they migrated through these cosine-Litov cycles with tidal friction. I would say the greatest caveat is, do these planets form in the same place? This is a disk subject to a tidal field coming from the binary, from the companion. I would say we have not a clear idea of how planets form under such conditions, if they form at all. So, well, yeah.
So this is the boundary which are strong, and that's the if there's no GR or any kind of two-body extended effect, boundary is going to precess as well, right?
You mean you said the binary? Oh, the binary itself is, yeah, it's precessing, yeah. Due to the
We'll just follow.
Yeah, so I mean, it's essentially,
So we'll follow the
right. The binary, the angular momentum of the binary is precessing around the tertiary that has most of the angular momentum. So in reality, it's precessing about the total angular momentum vector, but the tertiary has most. And the binary, the planet, is precessing around this vector. So it's,
doing this part of the Laplace plane. So just
Right.
precess around the boundary.
around the binary. So the Laplace plane itself is precessing with everything, but this precession is so slow, the binary around the tertiary, that the planet is able to follow it.
Is there any chance of transit?
Yes, I mean, the chance of transit is the same as with misaligned planets with the absence of the triple. Yeah, but it's a window. It's so when the planet orbit is, we're looking at it edge on, there's a chance for transit, but it will keep precessing, and then we'll miss it. Yeah, that is still happening. Yes, so I guess statistically, if you looked at a bunch of binaries, like all of them, for a year, you should like see.
The problem, I guess, is GR precession is so fast, or high precession is so fast, there's no precession of the boundary relative to the tertiary.
I see what you're saying. Well, but the upside, well, the upside, that's one, you're talking about the upside precession of the orbit, or the angular momentum. The angular momentum will always precess around the total angular momentum.
I guess that's true.
Right? So that what GR is doing is competing with the upsidal precession of the angular argument of pericenter. But the angular momentum vector is if it's misaligned with the equilibrium, it has to be moving respect to the equilibrium.
There's a chance of turning.
Yeah, there is a chance, yes. But it's, I guess it depends on how many binaries we look at at the same time. But yeah, I mean, we did find a misalignment of 3 degrees with Kepler 413, and we caught it in the act because it's going to stop transiting. So yeah, so there is, maybe the ETVs is not the best chance, maybe just looking at a lot of these, hoping that you get a oblique transit, yeah. Again, and I mean, I think the Laplace interpretation is pretty cool, but if we do see these things misaligned, we would learn a lot about planet formation. I mean, get real numbers of how frequently circumbinary planets form. If they form in these harsh conditions, it means that it's a really resilient process. So, if they are, well, we already know their form, but if they form like in a diversity of inclinations, right, it would be interesting. Because even that 3-degree planet, we're not sure if there's a tertiary there or not. So I don't know. Anyway, I will move on to circumbinary disks. And they're connected to, obviously, circumbinary planets. And I personally think that not only the usefulness of these disks not only goes in that direction in time, but actually can go the other way, because we don't know how these binaries form. These compact 0.2, 0.3 AU binaries, and maybe, Chris, you have some ideas on disk fragmentation and migration, but there are hypotheses, coefficient, dynamical capture, protostar disk fragmentation, but in reality, these binaries are kind of mysterious. And even the brute force approach of having a global simulation of star formation is not even close to getting these spatial scales. So if these disks are peculiar, and there are some indications that they can not only give information about how this happens, but maybe information on how that happened. And the disk mass might be the key clue. If you look at the sublimited flux of binaries with sublimited emission as a function of binary separation, we first get a decreasing trend, which is somewhat intuitive. Very separated binaries essentially act like singles, which are the black points. And as you start shrinking the separation, you start getting less and less gas and dust, and your sublimited flux decreases. And at separations of 10 AU, essentially you stop getting detections. However, there's this magenta population here. These are the disks I mentioned before, UZ tau east, DQ tau, spectroscopic Titori binaries. They have orders of, at least an order of magnitude more brightness than other binary disks. You can convert flux to mass with some caveats, but at least the tentative indication is that these disks could be very massive. And massive disks could have a major role in forming stars, even in the presence of these tidal fields, which is the work of Abrafikov and Silsby in the last couple of years, the role of the disk mass in winning over these external tidal fields. So what I like to focus on is in the type of disks in this category, compact stars that may lead to Kepler binaries with planets, and focus on the accretion properties of these disks and other things, but mostly I'm going to talk about accretion, these guys. So just general background, if you're interested in black holes, these simulations are similar to that. So very minimalistic in the physics point of view. I find something interesting between this duality between Titori disks and supermassive black hole binary disks is that we're sure these guys must exist, but they're really hard to observe, the black hole ones. And the Titori ones, we have them, we see them, but we're not quite sure how they form. So yeah, these are both very important problems. The black holes, especially for, well, to solve the last parsec problem, but also observationally for gravitational wave detection. So this is a collection of classical Titori spectroscopic binaries. And just like if you look at the orbital elements, they're quite varied. 0, eccentricity, 0.3, 0.6, mass ratios, some of them very close to 1, but this is actually 0.3. They span a fairly wide range of parameters, similar to the Kepler circumbinary systems. What I want you to focus here at this point is the variability in their accretion, or the variability in their accretion indicators. Some of them have equivalent line width variability. Some of them have photometric variability. One of them has even radio variability. So it's interesting to know what triggers this and why it is somewhat periodic. So people refer to this as pulsed accretion. So this is just one example of UZ tau east. These are the photometric light curves. These are the equivalent line width. If you do a spectral analysis of these light curves, you see peaks. You see a few higher. I don't know if they're exactly harmonics, but you see higher components, but you see a wide peak at what it is actually 20 days, the period of this binary. So we want to understand how simple this picture is, how periodic accretion onto a binary can be. So for that, we do simulations. And I am interested in just the technical aspects of the simulation. And these simulations, although they're very simple from the physical ingredients, they can be complicated in terms of the methods used. First, we want to follow the accretion onto individual stars. That's often complicated in codes using cylindrical grids. And we want the stars to be eccentric. So those are things that are easily done in SPH, less easily done in grid codes. So I thought this was a good experiment to try the moving mesh code Arepa, which some of you are familiar with, which tries to combine both elements, the quasi-Lagrangian nature of the code. So yeah, the basic paradigm, this is a classic paper by Andrew McFadden, how you trigger density waves in the disk, how the disk torques the binary, how you accrete onto the binary. And often these simulations, even the state-of-the-art ones, have a hole given because of the singularity of the coordinate system in polar coordinates. This is a Pluto simulation done by one of the grad students at Cornell working with me. What we want to do is turn this type of simulation into a simulation in which the gas is allowed to go all the way into the stars and measure individual accretion rates. And one of the problems in simulations is...
Two dimensions, 3 dimensions?
Two. So as simple as possible. So one of the problems is that we yet don't know which of the stars receives more mass if you have a mass ratio of not equal mass. So we would like to address that and how that accretion rate depends on what's happening in the disk. So this is just an Arepa simulation, moderate to low resolution with the hole. So you can, it's a grid code, so you can put a boundary, an open boundary, a diode boundary condition, such that the gas that wants to leave just leaves and no gas is allowed to enter. You want to see if these features and this eccentricity triggering and other things are consistent with what you would get if you allow the gas to move inside. So this is the case for a circular binary, which actually creates quite a bit of eccentricity in the disk itself. Classical paper, Artemovich and Luba used SPH. Other creative approaches by Gunther and Clay used a hybrid grid, just Cartesian in the center, polar outside. So people have tried to approach this system in different ways. Cartesian, all the way, very high resolution, only a few orbits is another approach. And probably the state-of-the-art in this problem is the DISCO code by the NYU group, in which it's like a super Fargo algorithm in the sense that you want to subtract the Keplerian motion in the disk, which gives you less truncation error and longer time steps. But what they do here, instead of subtracting that Keplerian motion, they're in practice letting the grid move in annuli, and they can adapt the wedges in resolution and radially. So what they put here is put lots of annuli where the binaries move such that they can capture the motion of the binary without having to have high resolution everywhere. So as a different approach, I want to use the moving mesh code Arepa, which is in some ways a conventional grid code using linear reconstruction within cells. The only difference is that the mesh itself is allowed to evolve, and you solve the equations of fluid dynamics in the frame of the moving phase. So use Riemann solvers, and it's a finite value method. So the only difference, to put it simplistically, is that you're doing Lagrangian Galilean boosts in every cell, such that you can take longer time steps and reduce the advection error across the phase. On top of that, since it's quasi-Lagrangian, if you have converging flows or accretion, your cells will converge and you get higher spatial resolution automatically. So as opposed to using a structured grid code, even if it is moving, is that locally the polar grid, it will still be Cartesian. So you still have some of the limitations associated to advection error across phases. So what we want to do is simply let the mesh evolve and have like a system like this in which the disk is moving and the cells are concentrating where the disks are. Well, okay. So this is what we want to do, measure the individual accretion, measure the shocks, the tidal features, and see if it makes sense or it's absolutely necessary to do the whole or not. So this is the same initial condition, which is an evolved system with a hole, and then I restarted allowing the gas to go inside. And you can say that overall, and I'll show you an eccentricity plot later, for a circular binary, the change is not that much. However, for an eccentric binary, you start finding greater differences. The hole is larger because the hole grows with pericenter, and although the initial conditions were identical, you quickly develop difference in the morphology of the gas. And this is because when you have an eccentric binary, you trigger this tidal wakes that actually have a significant positive velocity, radial positive velocity. So when the gas isn't falling, is constantly meeting tidal tails that are ejected from the inside. So the dynamics of the gas here can be very different from the ones with the hole. If you go to even higher eccentricities, just the difference are even more striking.
So what's the answer in terms of the where the gas is going?
Just 1 second, yeah. Well, if you want to know where the gas is going, so far, and this is preliminary, it seems that even the gas chooses a star, a preferential star. Okay, so well, this is the eccentricity. The eccentricity of the disk seems to follow some coherent pattern with the hole. So this is eccentricity, and this is the average argument of pericenter, and we see some semi-regular precession of the whole disk when the binary is circular. When the binary is eccentric, it's even messier, but you still can identify some structure. And to answer the question of accretion, let me show you this instead. In blue and green are the secondary and the primary, except that they're equal mass. So it seems that, and this is consistent with the disco simulations, it seems that the asymmetry of the disk makes the disk choose a star just randomly, to which it dumps a significant greater fraction of the mass. If you time average these light curves, the factor of mass that goes into the nominal primary of other equal mass is a factor of 3. And I've been trying to explore this evolution, integrating longer and longer to see if the precession of the inner cavity, because the inner cavity is eccentric, so it would precess with the binary. If the precession of the inner cavity can alternate which star gets more mass, I have not seen it. But that's a big challenge when you want to measure secular effects with a hydrocode. Just integrate thousands of orbits when you're following the gas onto the central stars. It starts becoming very, very expensive. So at this point, we're integrating of the order of 500 orbits when we resolve the binary.
What are the equal mass? What is the non-equal?
I don't know. Anyway, so this plot is to show that, however, if you change how accretion is deposited on the star, that is, if you have a hole instead of a sink particle that extracts material, that is an open boundary around each star, you get very sharp accretion features at each pericenter passage, as opposed to a viscous accretion that is smoothly extracted from the mini disks, which spreads out the accretion throughout the orbital period. And just to show Lagrangian trajectory, so these are Lagrangian tracers that start at the same cell. They essentially follow the same trajectory as long as they're in the disk. However, once they fall into the cavity, they follow trajectories that I was quite surprised about, especially because they seem that at least those cells that start there, or the gas that starts there, even though the gas that ends up in this star had to go through this star at some point. So the cartoon in which the disk has these tidal arms falling into the stars and depositing material smoothly seems to be too overly simplified, and maybe the accretion is actually much more complicated than we would like it to be. So this, I'm ending there. I'm going to leave the summary up there, and I would like to take some questions. Thank you.
So we have time for a couple of short questions.
Have they detected any modulation in the accretion rates?
I'm sorry?
Have they detected any modulation in the accretion rates?
Right. So well, if in the accretion rate indicators, so if the photometric variability of the stars that I showed you a spectral Lomskagel periodogram has a peak. The major peak is at the orbital period of the binary. There's an extra, and the extra modulation is sublimiter. And some people have suggested it's not accretion, it's actually magnetospheres touching. So it's non-thermal modulation. But there's modulation, absolutely. Yeah.
Are there any signatures that you can look for these planets that can be unstable Laplace surface and crash into the stars or get into?
You mean like polluted atmospheres? That's the only thing I could think, but as somebody pointed out, I'm integrating for a very long time scale, so it would be a strong function of, a sensitive function of the settling time and when you observe the binaries. So you would have to catch the crash in the act. Otherwise, I mean, that's what I like the survival hypothesis better because it's predictive. Otherwise, we're just saying the planets got ejected. But besides metal pollution onto the stars, I cannot think of anything else. No.
I'm surprised that when you integrate back to that question, that binaries actually get very high eccentricity during those oscillations. Isn't that also, I mean, put that into the secular code?
Right.
The M-body?
The M-body has an envelope, like a fuzziness on those curves. But I do have an M-body. I didn't put it there. I did check with a couple of cases with M-body. The reason the planet doesn't see the eccentricity is because the mass ratio is very close to 1. So the eccentricity, the force eccentricity in a coplanar system of the binary acting on the planet actually is proportional to the mass ratio. It's essentially the octuple term. The octuple terms goes to 0 if the inner binaries have equal mass. So eccentricity is conserved at the quadruple level. So if the binary had not unequal mass ratio and I included the octuple, then the dynamics would be much richer, and you would see a modulation of the eccentricity. Probably still somewhat small, but you would see instead of being a flat curve, it would have this force eccentricity on top of it.
Okay, I think we have to wrap up. And if you want to join us for cookies upstairs to follow up the discussion. Also, we're going to take Diego for the next time, so please let me know if you have any. Thank you.